So the directions for the standard problems at this point are if the series, or show whether the series converges or diverges, and if it converges, find its sum. So what we have focused on so far is we've talked about geometric series. And geometric series, we know when those converge or diverge because we're able to get a formula for the general partial sum. So 2 days ago, so 2 lectures ago, we went through using a system of equations to figure out what the partial sum Sn looks like for a geometric series. And then that let us figure out, okay, when do these converge and when do these diverge? And then we were also able yesterday to look at the sum, difference, and constant multiple of series. And so I think we didn't talk a whole lot about constant multiple, but the rules work the same way as basically for integrals. You can split addition or subtraction of series as long as no more than one diverge. So if you have a bunch of series that all converge, that are added up or subtracted, you can split them up. If you have one that diverges and the rest that converge, you can split them up and the whole thing diverges. If there's 2 that diverge, then you need to know more information before you know whether or not you can split them up. When you have a constant multiple, so we'll talk real quickly about that because I think we didn't explicitly say it. So if we have a constant c times a term ak inside of a sigma notation, that's the same thing as the constant c times the sum of ak. So you can pull a constant out. If the sum ak diverges, then the constant times that still diverges, as long as the constant's not 0. So 0 times infinity, that might be unclear, but for most constants, for any constant other than 0, you can pull the c out. 0 is kind of a weird example, so it would make the whole sum 0, and that would make it converge in the case on the left. But aside from that, any constant can be pulled out. It does not change whether or not it converges. If it does converge, it does change what it converges to. If it diverges, it might change why it diverges. So it might change diverging from infinity to negative infinity, or bouncing between 1 and 5 to -1 and -5, or something like that. So anyway, this is kind of what we've talked about so far. The reason we study geometric series first is because we're able to get a formula for the partial sum. And so the next type of series we're going to study is a series where we're also able to get a formula for the partial sum. And so these are a little bit weird, but we're going to look at this series, the sum k equals, we'll say 0 to infinity. We're going to do 1 over k plus 1 minus 1 over k plus 3. And so this is one where you have 2 things subtracted, so it looks like maybe you could split it up. And we don't have a good reason for this yet, but if you were to split it up, it turns out they both diverge, which means that we don't know based on that whether or not the original series converges. So we have not explained why they would diverge yet. If you did split them up, we'll learn that later today and next week. But if you split them up, they would both diverge. And so that would not tell us what happens here. What we can do on this problem is we're able to get a formula for the nth partial sum. So we're going to write out a formula for Sn, kind of like we were doing when we first started geometric series 2 lectures ago. So if I look at Sn, what that means is instead of the sum from k equals 0 to infinity, it's the sum from k equals 0 to n. And so n just we think of as being a very large number, so maybe it's a billion or something larger than that. But n is a very large number because what we want to end up figuring out is the limit as n goes to infinity, but n itself is a finite number. So we're going to plug in 0 for k and 1 for k and 2 for k up to n and see if we can determine what happens here. So if I plug in k equals 0 to that term, then I get in my work, I get 1/1 minus 1/3. Is everybody clear where I'm getting that? So I plug in 0 for k, and I get 1/0 plus 1 and 1/0 plus 3. So I get this setup. And then if I plug in k equals 1, then I get 1/2 minus 1/4. And if I plug in k equals 2, I get 1/3 minus 1/5. And now we're going to keep going, but does everybody follow where I'm getting those terms? Any questions on how I'm getting that so far? Definitely not done, but do we understand what I'm doing? Okay, and so if you look at what's up here, we're, like I said, we are going to continue, but if you look at what's up here, what happens with those numbers? So look closely at what we've got. What could we do? And you can unmute yourself and tell me, or you can say it in chat, but let's try to look for something that would happen here to make this easier.
Common denominator.
You could get a common denominator, not what I'm looking for. So we're going to see why we don't actually want to do that yet. But good guess. Okay, let's keep going and see if we notice in a second. So we're not noticing yet, no problem. So k equals 3. That gets us 1/4 minus 1/6. So look at the fractions we've got and see if there's anything we can do to this to make it a little bit easier.
Is it
Like cancel some stuff.
Yeah, some stuff cancels. What cancels here? I know a couple of you were talking on the who, but somebody, you can keep going. It's okay. What cancels?
The 1/3 and the 1/4.
Yeah, the 1/3 cancel and the 1/4 cancel. So 1/3 is negative here and is positive here. That cancels. The negative 1/4 cancels with the positive 1/4. So if we keep going, let's see what happens. So if we go to k equals 4, now I've got, okay, 1/5 minus 1/7. Remember, I'm plugging this in up here. So now what happens at this stage?
the 1/5 would cancel?
The 1/5. So I'm going to actually do that in green. What happened now, though, that hasn't happened before that? So there's been some stuff that's canceled. So the 1/3 canceled as soon as we got this one, even though maybe we didn't notice it yet. But the 1/3 canceled here. The 1/4 canceled here. The 1/5 canceled here. What now happens with that green canceling that had not happened prior to that? That's kind of
all of K2 is gone now.
Yeah, the whole k equals 2 term is gone. So I'm going to extend this one more term. But if I go to k equals 5, then okay, I get 1/6 minus 1/8. And now, okay, so that's k equals 5. And now the 1/6 is canceled. And now the entire k equals 3 term is gone. Does everybody see that? Everybody see what's going on? Okay, so it seems like everything's going to cancel out. And so we're going to keep going, but remember that we're talking about Sn. So like as we go up, like on the next one, 1/7 is going to cancel. Does everybody see that? And then 1/8 is going to cancel. These two are not, because we're getting, the denominators are getting bigger. So this 1/1 and 1/2, those aren't canceling, but these are going to cancel. So even though we haven't gotten to it yet, the 1/7, and I'll do a dashed line, is going to cancel as we go, and the 1/8 is going to cancel as we go. So what I want to do is go to the end of the sum. Remember, we're doing a finite sum. We're not actually going to infinity when we're talking about Sn. Sn's just a big number. So maybe n is 100 or 1,000,000 or something like that. So k equals n is the last term in this expansion. So we're going to come to the end of the sum and write out what it looks like when k equals n. And so I'm plugging n in for k. So we get 1/n plus 1 minus 1/n plus 3. And that's the last term in the nth partial sum. So like if this was n equals 100, this would be 1/101 minus 1/103. All right, but it's for whatever n is. And so now we're going to go backward. So if k equals n is the last term, what k value would be the term right before that. K equals what?
N minus 1.
N minus 1. So we're going to go back and say, okay, k equals n minus 1. And that's the idea that, okay, if this is 100, then this is 99. If this is a million, this is 999,999. And so it's one less than whatever this is. So if I plug in n minus 1, I get 1 over n minus 1 over n plus 2. So again, the way I'm doing that is I'm replacing n, or I'm replacing k with n minus 1. So it's n minus 1 plus 1, which is n, and then n minus 1 plus 3, which is n plus 2. Does that make sense to everybody? Okay, now we're going to go back again. So right before that is k equals n minus 2. And so, okay, n minus 2 plus 1 is n minus 1. N minus 2 plus 3 is n plus 1. And now we're going to cancel stuff as we can. What at the end of this sum cancels so far?
1 over n plus 1.
Yeah, the 1 over n plus 1s cancel. So we can get those to cancel. We're going to keep going back and see if we can get an entire term to cancel like we did going forward. So if we go backward, k equals n minus 3 gets us 1 over n minus 2 because it's n minus 3 plus 1. And then this one gets us n minus 3 plus 3 in the bottom. So it's 1 over n for that one. I'm going to slow down for just a second, but everybody make sure we understand where those terms are coming from. This becomes pretty easy, but it's very weird at first. Any questions on where I'm getting these so far? Okay, now what else cancels with what we've got on the screen so far?
1 over n.
1 over n, good. And so the 1 over n cancels. Now what we're going to do is we're going to keep going back until an entire parenthesis, an entire term cancels out. So one of these we're looking for to cancel. So we go back, that hasn't happened yet. We go back to k equals n minus 4. So okay, n minus 4 plus 1 is n minus 3. N minus 4 plus 3 is n minus 1. So now if we cancel again, we get 1 over n minus 1 canceling. And now this entire n minus 2 term has canceled out. So when that happens, we continue to go backward and we say, okay, and so on back. So we're coming from the front, we're going 4, 5, 6, 7, 8, 9, 10. We're getting these to cancel. From the end of the series, we're going backward. The next one's going to be n minus 5, n minus 6, n minus 7, back until 5, 4, 3, 2, 1. So, okay, by continuing backward, what else on the screen will cancel by continuing to n minus 5 and n minus 6 and n minus 7, and what will not? So first question is, what will cancel that I've got on the screen by continuing backward? What else will cancel that's there?
All of
Everything
k
else.
equals n minus 3 and all of k equals n minus 4.
Yeah, so these are going to cancel. These two are not, because the denominators as we go backward are getting smaller. So this one is going to cancel. So I'll put a dashed line through it, meaning, okay, I don't actually have that on the screen. But if I continue the pattern backward, it's going to. And same thing with 1/7 and 1/8. I don't actually have that on the screen, but if we continue forward, that's going to cancel. Now, we don't continue forward after this. So these two are still there. But what this tells us is that then Sn is equal to 1 over 1 plus 1 over 2 minus 1 over n plus 2 minus 1 over n plus 3. So this formula is now a closed formula for any partial sum. If I wanted you guys to calculate, so let's say on a test, I gave you this question. So calculate this sum, which may very well happen. or find the sum. And so this purple is not this question, but if I wanted you to find the sum k equals 0 to 150 of 1 over k plus 1 minus 1 over k plus 3. So if that was a test question for you guys, I would expect you to do this, and then how would you find the sum from there?
Just plug in 150 for n.
Exactly. You plug in 150 for n. This is giving you any partial sum. Well, this is S150. So that's S150, which is 1 over 1 plus 1 over 2 minus 1 over 152 minus 1 over 153. And the point of a test question like that would not be, now please add those. Without a calculator, I would not want you to get a common denominator and deal with that, but I would want to know that you knew how to get this. Does that make sense to everybody? Everybody clear so far?
Yeah.
Okay, that's
so
kind
would
of
a question like that have multiple choice answers on a test?
I'm sorry, say it again.
Would a question like that be more likely multiple choice since you're not asking for a specific number?
No, WebAssign would take this and understand that it was equal to the right answer.
Okay.
So yeah, like I have no idea what that is, but please don't spend time trying to find a common denominator. Just type that in.
Got it.
You might make this 1 instead of 1 over 1, but whatever. I'm leaving it as a fraction because in general it's going to be a fraction when you have one like this. But like obviously this is just 1, but it doesn't matter. It will take 1 over 1 as well. Other questions so far? Okay, now that's not the question. Oh, I'm sorry. Go ahead.
I'm sorry.
You're good. Go ahead. Whoever that was. I'm sorry, I don't know who it was. You guys good? Okay. Okay. So this purple part is not the question we're actually asking. We're trying to go 0 to infinity. So, okay, given though that this is any nth partial sum, how can we use that to determine whether this infinite sum converges? What do we want to look at?
Since it's 1 over, the denominator gets bigger.
Yeah, so we're looking at why does the denominator get bigger? We're looking at what this does as what happens. As n does what?
Goes to infinity.
As n goes to infinity. So this series, remember the definition of a series is the limit of the partial sums. So we want to know what is the limit as n goes to infinity of Sn. Well, that's 1 over 1 plus 1 over 2 minus 0, because these are 1 over infinity. So then, okay, that goes to 1.5, which is 3/2. So this original series converges to 3/2 because these terms go to 0. Does that make sense to everybody? So the infinite answer may actually be simpler than doing this, but this kind of represents, do we really understand what's going on here? So this is a formula for the nth partial sum. This is how we can use that for a random other problem. But to find the infinite sum, this is how we do it. Any questions on this problem? Okay, a couple comments. One is, this is an example of what's called a telescoping or a collapsing sum. Or a telescoping or collapsing series. So this is a telescopic series. Kind of the idea is, okay, it collapses down like an old telescope would. And so all of these middle ones cancel out and you're left with some stuff at the beginning. You're left with some stuff at the end. Now, if you're looking at just the top line of this Sn, so everybody kind of look at that for a second. This line, it looks like when you just say plus and so on, everything is going to cancel forever. And so then, okay, why don't we just say, okay, well, then it's 1 plus 1/2. And the reason for that is because any nth partial sum does have leftover terms. And these terms at the end, those terms are what determine whether or not there is a sum. So these determine whether or not the sum converges. Because these went to 0, that meant this sum did converge. And then because these were 0, these were the only one that mattered. If these did not go to 0, then it's possible the sum diverges or it would go to something else. So these determine that there is actually a sum, or maybe that there's not actually a sum. If there's not one, it diverges. So like if these were to go to infinity or something, the whole thing would diverge and then these wouldn't matter. If these do go to zero, which is pretty common, if these do go to zero, then okay, it'll converge to whatever these add up to. Does that make sense to everybody? All right, but the end part of this is very important because that's what shows whether there's a sum or not. Let's do another problem like this. So the directions, I think I've still got it copied. I'm going to try to paste in the direct, well, maybe not. Yeah, it's not going to work. Okay, anyway, same direction. So show whether the series converges or diverges. And then if it converges, find its sum. So we're going to do the sum k equals 2 to infinity of natural log of k over k plus 1. And so now this ends up being a telescoping sum, but you have to notice that you can rewrite it this way. So we're going to actually start by saying, okay, well, this is the same thing as the natural log of k minus the natural log of k plus 1. Does that make sense to everybody? Okay, so because you have division in a log, then you can do that. This ends up being a telescopic sum. So we're going to start with Sn. So we're going to go with k equals 2 because that's where this starts. And we're trying to get a formula again for the nth partial sum. So if I plug in k equals 2, I get natural log of 2 minus natural log of 3. Now I go to k equals 3. And I get natural log of 3 minus natural log of 4. And now remember, we're looking for things to cancel. So at this stage, natural log 3 cancels out. Now we're going to continue in general. So up here, we went a little bit further on the top line than what we needed to. We need to continue on these until one single entire term cancels out. And then it's clear, okay, they're going to continue to cancel until the very end. So we're going to go to k equals 4, and we're watching for an entire term to cancel out. So if I go to k equals 4, then I get natural log 4 minus natural log 5. Well, now the natural logs of 4 cancel out. And now this entire k equals 3 term has canceled. Does that make sense to everybody? You guys good? Okay, by continuing, so when I go to k equals 5, k equals 6, and k equals 7, what else that's on the screen is going to cancel?
ln of 5.
The natural log of 5 will cancel, good, but the natural log of 2 will not. So I usually just indicate that with a dashed line, meaning, okay, that's going to cancel next, but natural log of 2 won't. So now we go to the end of the series. Is everybody clear why we don't need to continue at this point once we get this whole thing to cancel? Does that make sense? Okay, so now we go to k equals n, which is the last term in the series, or the last term in the partial sum. So k equals n. That gets us natural log n minus natural log of n plus 1. And now we go backward. So we go to k equals n minus 1. That gets us natural log of n minus 1 minus natural log of n. And keep in mind, we're plugging these in up in the original, well, the rewritten form of the original series. So log n minus 1 and then log of n minus 1 plus 1 is log of n. That's where that's coming from. And now we're watching for things to cancel again. So natural log of n cancels with natural log of n. And now we continue backward until an entire term cancels again. So if we go back one more, then okay, we get natural log of n minus 2 minus natural log of n minus 1. And now the natural logs of n minus 1 have canceled. We stop writing terms, or we can stop writing terms because the entire n minus 1, k equals n minus 1 term has canceled. By continuing backward, n minus 2, the log of n minus 2 would cancel, but the log of n plus 1 at the end would not cancel. Okay. And then I just saw that somebody asked a question in chat. I'm sorry, I missed it. I will address, that's about the first question, I think. Yeah. And so we'll talk about that in just a minute. My fault, Justin. And I didn't mean for it that you can only chat to me privately. If you want to post something publicly, you're welcome to. I just changed that. All right. Let's finish this example and then I'll go back and get to that question. But does everybody follow this? Any questions so far here? Oh, my bad. Okay, so would you get the same answer if you use the original equation instead of splitting it? Technically, yes, Micah, but you need the subtraction. So the question is, would you get the same answer if you use the original formula instead of splitting it? You need to see the stuff canceling out. So at some point, you've got to notice that like these cancel. So you're going to need to use that log property. I don't know that any of us, including me, are probably good enough at logs in this form unless you change it to subtraction to notice the stuff cancels out. Do you see what I'm saying? So,
yeah.
So you probably do need to split it at some point. And then if the original only has one term not canceled, will the infinity term only have one not canceled as well? Yeah, because of the way these break down. Maybe there's a real weird situation I'm not thinking of, but yeah, these are basic. They're like symmetric basically. So like whatever's left over here, it's going to be the same here. But you should always work it out to make sure. Does that make sense? Okay. Okay, so let's talk about a few more things with this here in a minute, but let's finish up this example. So Sn then is equal to natural log of 2 minus natural log of n plus 1. So now we're looking at this. Remember that when we're talking about the infinite sum, we're going always to infinity. And so we're looking at the limit of this as n goes to infinity. Well, as n goes to infinity, the natural log of 2 does not change. What happens to the natural log of n plus 1 as n goes to infinity? So remember, the natural log graph looks like this. So as n goes to infinity, log of n or log of n plus 1 is also going to go to infinity. So this actually approaches negative infinity, which means the series diverges. Does that make sense to everybody?
Wait, why does it approach negative infinity? Just because of natural log of n plus 1?
Yeah, because natural log n plus 1 goes to infinity. So you're taking a finite number minus infinity. So then it's negative infinity. Does that make sense, Gavin? Okay.
Yeah.
Okay. Other questions so far? Okay, so here again, this is where it's real important that this last term, you figure out what the end of the series looks like. The natural log 2, like if you just start at the beginning, it looks like, hey, that's just going to be natural log 2 and everything else is going to cancel. The problem is any partial sum always has this leftover term. Well, this time that leftover term is approaching infinity, which makes the whole series diverge rather than converge. Okay, and so a couple things about it. Any other questions so far on just how to do this process? Yes, following what's going on? Okay, and so one of the questions in chat about the first question is, how would it change if the limit was negative infinity? And on this expression, it would not change. So as the limit of n goes, the limit as n goes to negative infinity of this, these would still go to 0. But on a series, we're always going to be going to positive infinity. Does that make sense, everybody? Okay, but if it were for some reason going to negative infinity here, these would still go to 0 because it's 1 over a huge, huge negative number in that case. Okay, the other thing is, this is, how weird is it for this to happen? like, does everybody see what's going on? Like, this is going 1, 2, 3, 4, 5 in the first fraction, and then it's going 3, 4, 5, 6 in the second fraction, and 1 is positive and 1 is negative. And so that's why this happens. And then here, same deal. Like the first one's going 2, 3, 4, 5, 6, and the second one's going 3, 4, 5, 6, and one of them is plus, one of them is minus. So these problems are very, very artificial, meaning they are made up so that this happens. Does that make sense to everybody? Like this has to be very, very specific for this to work. Like if there was any sort of difference, if this was a plus, this wouldn't work at all. You have to have 1 plus and 1 minus. And so the terms have to catch up with each other. Like these become these, and that's why they're canceling. So the point of saying that is, first of all, these examples are kind of crap. They're made up to study this way. And that's not to say it's not important. It is. The reason that it's important is because we're able to get this formula for this nth partial sum. Whereas for most series, we cannot do that. So geometric series, we were able to 2 days ago come up with this formula for the nth partial sum using a system of equations. For telescoping series, we're able to use this pattern in order to come up with this formula for the nth partial sum. After this, so after today, most series, we're not going to be able to get a formula for the nth partial sum. So like when you're asked to do these problems starting next week, when it's doing this, so show whether the series converges or diverges, that'll be it. We're not going to be able to find the sum. We'll just know there is one. So if it converges, there is one. And then you can use a computer to approximate the sum. You know, if you've done any sort of programming in MATLAB or Java or any computer science class, or even if you used Excel, it would be easy to program something to add this stuff up. You can use a for loop in any programming language to do this, or in Excel, you can make a column 0 to 10,000 if you want, and then make the right-hand column calculate these terms and then just sum the column. And so what the idea is later is, okay, if you prove it converges, there is a sum. So then, okay, if you add a bunch of terms, you can approximate what that sum is. But the reason we study telescoping series is not because of like earth-shattering applications. My guess is, and maybe I don't know, maybe I'm not aware of an application, but there's probably not a whole lot of applications of telescoping series. There are lots of applications of geometric ones, but this is another example where we're able to come up with this, which is why we study these. But they are very artificial. Most of the time when you have something that looks like this isn't going to happen. If I made a small change, if this was 1 over k plus 1 and this was 2 over k plus 3, it's nothing like this because nothing's going to cancel out. Does that make sense? Does everybody understand what I'm talking about? Okay. Any questions on telescoping series? Are we good on these?
For the first question you did, that's on the screen right now, you mentioned that if you split it up, both of them would diverge. Can you?
Yes, and that's actually what we're getting into next, Gabby.
Okay.
So I'm glad you asked that. That's going to be the next topic. All right. So the question, I think, sorry, I interrupted you, Gabby, but the question I think you were going to ask is, okay, you split them up. How do we know those two both diverge? Turns out they do. And so yesterday we were talking in class about if you split them up and they both diverge, we don't necessarily know what happens. Does that make sense? So like when you split up two series and they both diverge, then the original series could converge, which here it converges to 3/2. Down here as well, if you split it up, they both diverge, and we'll talk more about that later. But if you were to split these, they both diverge, and then the original diverges, which makes maybe more logical sense, but it doesn't in general have to happen that way. Does that make sense? Okay. Other questions so far, you guys? All right. So real quick, this series. What does that series do? Does that series converge or diverge?
Converge to 0.
The sequence converges to 0, but the series does not converge to 0. It does converge, but the sequence converges to 0. So like the next thing you're adding is 1 over 128 and then 1 over 256. that sequence goes to 0. But this is the series. That series. Does everybody see that? Okay, so remember that when we're talking about these, and I'm glad you said what you said, you have the sequence 1/2 to the n, but then you have the corresponding sequence of partial sums, k equals 0 to n of 1/2 to the k. And so the sequence on the left does in fact go to 0. That's completely correct. Why does this series though converge? What type of series is it? Excuse me. Why does this series converge?
Because it's geometric and 1/2 is less than 1.
Yeah, it's geometric and the common ratio is less than 1, or the absolute value that's less than 1. So can we find the sum of the series? Can we figure out what it converges to?
Yes.
Yeah, so it converges to a over 1 minus r, which is 1 over 1 minus 1/2, which is 2. And so then, okay, that's 2. Does that make sense, everybody? We good? Now think about what we're saying, okay? We are saying 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1 over 32 plus 1 over 64 plus 1 over 128 plus 1 over 256 forever. You're adding forever an infinite number of positive numbers, and you get 2. How is that remotely possible? If you add infinity positive numbers, why is that not just infinity? How is it as small as 2?
Because you're adding half of the previous amount.
You're adding half the previous amount, yeah. And so then, okay, logically though, still it's a positive number. What you said is not wrong, but it's still a positive number. Why is that not infinity?
Because
You're
you
right.
can never create greater than 1.
Because what? Say it again.
If you add half of the previous, you can never create a number greater than 1.
Yeah, okay. And the numbers that you're adding, by the time you're at these late numbers, what are they? Like when you're at the billionth
They're infinitely
term,
small.
they're infinitely small, meaning you're adding basically what?
0.
You're eventually basically adding 0. Does that make sense? Like, so you're adding half, and I don't know if you've ever heard of the problem where they talk about like, I don't know what it is, an ant or something like walks halfway across a room every hour. And so like, okay, you walk another halfway across the room every hour and never gets to the other side because you always just cover half the distance. Does that make sense? Same idea here, 1 plus 1/2 plus 1/4 plus 1/8. You get to 2 eventually, but no partial sum will ever be 2. Does that make sense to everybody? The limit is 2. And so that's real weird to think about. But the reason that's possible is because eventually what we're doing is we're adding 0. So what if I added something like this? So what if I were to add 0.01 plus point, and we talked a little bit about this already. If I add that infinitely, then what happens?
Goes to infinity.
That goes to infinity. Does that make sense? So, okay, so if I have some series, so remember we've got the sequence and the series. The sequence here, AN, goes to 0. That allows this not to go to infinity. It doesn't mean it has to not go to infinity. We don't think, or I don't think, but the fact that this sequence goes to 0, the things that you're adding eventually are basically 0, means, okay, this is not completely weird. It's weird, but it is not completely weird. So what if I had this? So if I have the sum AK, k equals whatever to infinity, we'll say 0, but the sum of AK, if the limit of AK what if I told you the limit of AK is 4? So the things you're adding approach 4. What happens to the sum then? So in the long run, you're doing 4 plus 4 plus 4 plus 4 plus 4 forever. What's the sum? If this is true, what's the sum?
Infinity.
Infinity. What if the limit of AK is -4. And in the long run, you're doing -4 plus -4 plus -4 plus -4 forever.
Negative infinity.
It's negative infinity. What if the first term's really huge? Like, what if the first several terms are 80 billion or something like that, and the limit is -4? Is this still negative infinity? Yes, because if you have millions and millions of these, you're going to pass up 80 billion by a lot. Does that make sense to everybody? So if you're trying to determine whether or not the series converges, the beginning doesn't matter for whether or not the series converges. It does matter for what it converges to, but it does not matter for whether or not it converges. If the limit of the sequence is 4, the series automatically diverges. If the limit of the sequence is -4, the series automatically diverges. What if the limit of the sequence is something really, really small? So what if eventually all the terms, they're not quite 0, but they're really close? What's the limit of that sequence?
Well, every 10,000 of them is 1. So
Every
you're still
10,000 of
adding.
them is 1. And so you're still adding an infinite amount. So what's it do?
Diverges to infinity.
It diverges to infinity, even if the first terms are huge, or even if the first terms are like -80 billion. You get trillions and trillions and trillions and trillions of these, and that goes to infinity. Does that make sense? So then what would have to happen here for this to possibly converge? If this is going to converge, what does the sequence have to do?
Limit 0.
Has to go to 0. Does that make sense? Okay, the limit of this sequence must be 0. Otherwise, the series has to diverge. That's a huge, huge deal. Does everybody understand that? Okay, remember there's a sequence. The sequence is the list of things that you are adding. The series is the total of all of those. If the terms that you're adding do not approach 0, then the series must diverge. Does that make sense? Okay, big deal. So we're going to write that out in a big box. So we're going to say if the limit as k approaches infinity of AK is not 0, then the sum k equals 0 to infinity of AK has to diverge. Huge, huge deal. Okay, if the limit of the sequence is not 0, then if we add it up infinitely, it must diverge. This is called the K-term test. Or it's called the test for divergence. And you may see both of those terms used to call this. Some books will call it the N-term test because they'll use the letter N instead of K. I think our textbook that we're actually using calls it the test for divergence. I usually call it the K-term test. Whatever you want to call it, K-term test, N-term test, test for divergence, all that's the same. It means if the limit of the sequence is not 0, then the series must diverge. Does that make sense to everybody? We clear? Now I want you to read it very, very carefully. What does it say when the limit of the sequence is 0? So if we know, good answer. So if the limit of the sequence is 0, what does it tell you about the series? Somebody just said it, but
it doesn't tell you anything.
It does not tell you anything. If the limit of the sequence is 0, this does not apply. Maybe it converges, maybe it diverges. We do not know based on this. But if the limit of the sequence is not 0, then we know the series diverges. Does that make sense to everybody? We clear? Okay, huge, huge deal. So now, oh, my bad, I'm ignoring chat. Okay, but I think we've addressed that stuff. So good. All right, my bad. All right, so I want to look at this series. This is a real important series. Okay. So that series, first of all, what's next in the series? What's the next thing we add?
1/6.
1/6, then 1/7, and then 1/8. So, okay, is this a geometric series? Not a geometric series, because to go from one term to the next, you do not multiply by the same thing. Is it, so it's not a geometric series. Is it telescoping? Like if we watch for stuff to cancel, is a bunch of stuff going to cancel out?
No.
No, because nothing's negative, right? So, okay, this is not geometric. It's not telescoping. So we haven't studied it yet. If I wrote it this way, it should not be a big stretch to understand we could write it like that. Does everybody kind of see why? We don't start at 0, but because 1/0 would be undefined, but it's 1/1, and then 1/2, and then 1/3, and then 1/4, and then 1/5. Does that, everybody understand that? Okay, now remember, we've got the sequence and the series. The corresponding sequence is 1/n. What's the limit of that sequence? What's the limit of the sequence as n goes to infinity?
0.
0. So the limit of this is 0. That's just saying, okay, the list of numbers 1, 1/2, 1/3, 1/4, and so on, that list of numbers goes to 0. So then, okay, what does the K-term test tell us about this series? So the sequence goes to 0. What does the K-term test say about the series?
It could potentially converge.
Yeah, the K-term test does not say anything. It could converge, but it could diverge. So you're right. The K-term test does not tell us. Does that make sense? Everybody clear? Okay, so what we're going to do is we're going to do something real weird with this. And what I'm about to do, again, it's kind of like what we were saying 2 days ago. This is the theory part that I actually do need you to understand. So doing what we're about to do is something that you need to be able to do because we need to understand the theory. But it's not what we would normally do for this in a standard problem. Does that make sense? So this is the rationale behind what we're going to do in a little bit. But I do need you to understand it. So definitely follow it. It's just what I'm going to write now is kind of like the system of equation stuff 2 days ago. I do need you to understand that, but we don't do that on those problems. Does that make sense to everybody, what I'm saying? Okay, so what we're going to do is we're going to try to figure out what this sum does. And so we're going to look at several partial sums. We're not going to be able to get a formula for Sn, but we're going to look at some partial sums. So like S1 means the sum from 1 to 1 instead of 1 to infinity. Well, that's just 1. That means you plug in 1 and then you stop. And so it's just 1. And so then, okay, S2 is 1 plus a half, and then you stop. Does everybody see what I'm doing to get that? Okay, now we're going to actually skip S3, and then we're going to put S4. And S4 is 1 plus a half plus a third plus a fourth. Please ask if any of this is unclear as far as how I'm getting these. Okay, and so then actually I'm going to jump to S8. And so S8 is 1 plus a half plus a third plus a fourth plus a fifth plus a sixth plus a seventh plus an eighth. And then I'm going to put one more on the screen. I'm going to put S16 on the screen. And that's 1 plus a half plus a third plus a fourth plus a fifth, sixth, seventh, and eighth plus 9, 10, 11, 12, 13, 14, 15, 16. All right, now we're going to talk about these a good bit, but I want you to look at the partial sums that I'm putting on the screen. And if I were to get the next one that I would want to talk about based on what I've got there, what do you think the next relevant one is? If for some reason these are relevant, I haven't said why these are relevant, but like given what I've got here, what do you think the next one that I would talk about would be?
S of 32.
S32. These are powers of 2. So it's like 2 to the 0, 2 to the 1, 2 squared, 2 to the third, 2 to the fourth, 2 to the fifth, 2 to the sixth. And this is something we're going to look at because of what we can tell from the powers of 2. It's not that there is no S17. There is. There's also an S15 and an S14. But this gives us some insight as to what's going on in the infinite sum. So, all right. So I need everybody to just watch the screen for a minute and think through what we're about to do. Because like I said, it's weird. So I'm going to start looking at S4. Okay. And I'm going to group these. So of those two, which is the smaller fraction? Is 1/3 or 1/4 smaller?
1/4.
1/4 is smaller. So, okay, 1/3 plus 1/4 is bigger than 1/4 plus 1/4. Does everybody see why that's true? Because 1/4 is the smallest one, right? But 1/4 plus 1/4 is 2/4, which is a half. So this is bigger than a half. Does everybody see that? Okay, now that's still true down here. We've got this 1/3 plus 1/4, and that's bigger than a half. Clear? Now, what about these four? What's the smallest of those? Of the four in the parentheses, which is the smallest fraction?
1/8.
1/8. Good. So all of these are bigger than 1/8 except that one, which means this is bigger than 1/8 plus 1/8 plus 1/8 plus 1/8. But what is 1/8 plus 1/8 plus 1/8 plus 1/8? 4/8, which is then a half. Does that make sense? So the parentheses here, that's bigger than 1/2. Does everybody see why that's true? We good? Okay, so this sum S4 is bigger than 1 plus 2 times a half because it's 1 plus 1/2 and then another half, but it's bigger than that one. So it's bigger than 2 halves added to this. This is 1 and then, okay, 1/2 and then another 1/2, but bigger, and then another 1/2, but bigger. So this one's bigger than 1 plus 3 times a half. Does everybody see that? Now down here, okay, we've got 1, and then we've got exactly 1/2. And now this one's bigger than a half, right? These 4 added up are bigger than a half. Now, what about these? What's the smallest of these? Smallest of all these in parentheses at the end, what is that?
16.
1/16. How many are in this parentheses? How many fractions are there?
8.
8 of them. So it's bigger than 8/16, which is bigger than a half. So this one's bigger than 1 plus 4 times a half. So everybody see that? S32 is going to be bigger than 1 plus 5 times a half because we're going to have all these, but then we're going to have 17 through 32. Well, there's 16 of those that are all bigger than 1/32. So it's bigger than 1 over, or it's bigger than 16 over 32, which is bigger than half. So it's 1 plus 5/2, 5 times a half. It's bigger than that. And we can say, if we want to be more comfortable, we can say greater than or equal, but it's for sure greater than. But now it holds here too. If we put greater than or equal, it's 1 plus 1 times a half. And this one's greater than or equal to 1 plus 0 times a half. Does that make sense? Okay. This is 2 to the 0. This is 2 to the first. This is 2 squared, S sub 2 squared. This is 2 to the third, 8 is. 16 is 2 to the fourth. 32 is 2 to the fifth. And so S sub 2 to the n is bigger than 1 plus n times a half. Does that make sense? What does that mean about the series? It's a lot of complicated symbols, and it's a weird, relatively complicated argument. But why is this important? So if I add up 32 terms of this series, so if I go 1 plus a half plus a third plus a fourth plus a fifth up to 1 over 32, that is bigger than what, 3.5? Everybody see that? Okay, if I go to 64, it's now bigger than 4. If I go to 128, it's bigger than 4.5. If I go to 256, it's bigger than 5. If I go to 512, it's bigger than 5.5. So what happens?
Diverges.
Yeah, okay. Yeah, it diverges. Okay, Colin, so can we explain it again? Yes. So let's look at what's going on here. So we've got, everybody kind of look at it for a minute. So do we see why each set of red parentheses, those are bigger than 1/2? Does that make sense? Because this is bigger than like 1/4 plus 1/4. This is bigger than 4/8. This is bigger than 8/16. And so if you look at like 1 plus 4 times a half, you've got 1 here, you've got a half here, you've got another half here, but bigger. You've got another half here and another half here. So there's 4 halves there. And so this is bigger than or equal to 1 plus 4 times a half. Does that make sense to people who are asking that in chat? Can you just confirm that you understand what I'm saying? Everybody clear? Okay. Now I know it's weird, but then, okay, the reason that means that then this diverges is because eventually this gets as big as you want. If you want to add these up and make the sum bigger than 1,000,000, then you can do that. If n were 2,000,000, this would be bigger than 1 plus 2,000,000 over 2. Does that make sense? Now you would need 2 to the 2,000,000th terms, which is a ton of terms. 2 to the 2,000,000th power is a huge, huge number. But if you add enough of these, you can get the sum bigger than 1,000,000. If you want to get the sum bigger than 1,000,000,000, you need maybe less, but you need, if you use 2 to the 2 trillionth terms, then eventually that sum is bigger than 1,000,000,000,000. Does that make sense? I think I said 1,000,000,000, 2 to the 2 billionth terms then. That is really weird to think about, but that means eventually this sum gets as large as you want. So this goes to infinity. Okay, the sequence goes to 0, but the series goes to infinity. Somehow that means we're eventually adding 0 plus 0 plus 0 plus 0, and we're still getting infinity. That's very weird, but this is a huge, huge deal because it's kind of the first classic example. It's kind of the main, example we look at where the sequence goes to 0, but the series goes to infinity. This series is called the harmonic series. Okay, the harmonic series diverges. When we talk about like geometric series is a type of series. The harmonic series is not a type of series. The harmonic series is this one. Does that make sense? It's a famous example because it's the first classic example where the sequence goes to 0, but the series diverges. Everybody clear so far? Now, I do want you to understand this proof, but from now on out, we will accept as fact that this series diverges. And unless you're asked to show this proof, then you can give your rationale as the reason it diverges is because it is the harmonic series. And remember, harmonic is not a type of series, it is that series. So when you have this series, you can tell me, okay, I know this diverges because it is the harmonic series. Does that make sense to everybody? Any questions so far? That's good. Okay, that is the first kind of counterexample to the thing that seems like it would be true. So it seems like it would be that, okay, if the limit of AK is 0, then the sum converges. That's not true, because here the limit of the sequence is 0, but the sum diverges. Here, so if I have this one, we already said that's 2. It's a geometric series that converges. This is infinity. That's the harmonic series. Now that, like I said, is a huge, huge deal. It's counterintuitive. Here you're adding a bunch of stuff that gets smaller and smaller. What you're adding is approaching 0, and somehow you get 2. Here we've got some extra stuff, like you have a third, and then you have a fifth, a sixth, and a seventh in there. You have some extra fractions, but they're still pretty small. And somehow you don't just jump a little bit, you jump from 2 to infinity, which is weird. That is weird to think about, but that is true. These are 2 different sequence or series where the sequences do go to 0, but the series do 2 completely different things. The sum of this approaches 2, the sum of this approaches infinity. Huge, huge deal. Question so far? Everybody good? Okay, I want to do one example before we move on, and then I want to talk about what's coming up next. All right, so I think the only example we've actually done, no, we've done 2 telescoping series. This is not really an example. This is a proof of the harmonic series. And question 3 then is the sum, and actually we're going to put 4 problems up here. The sum k equals 2 to infinity of 5k minus 1 over 6k plus 5. And then number 4 is the sum k equals 2 to infinity of 5k minus 1 over 6k squared plus 5. And so I want to work both of these. And when we're approaching series, so again, directions would say, show whether this converges or diverges. If it converges, find its sum. We've got geometric. We've got telescoping. We've got the K-term test. And then we've got the harmonic series. And again, the harmonic series is not a type of series, but it is that series. And so this one is not geometric, it's not telescoping, it's not the harmonic series. Same thing here. So the only thing we know how to do at this stage is check the K-term test. Does that make sense? Okay, so K-term test says if the limit of the sequence is not 0, then the series diverges. So we check the limit of the sequence. So the limit of the sequence is 5 over 6. Does that make sense to everybody? Because biggest term on top is 5k, biggest term on bottom is 6k. That is the sequence, not sigma. So that's the sequence that we're adding. So then what that tells you is eventually we're adding 5, 6 plus 5, 6 plus 5, 6 forever. So what does the series do? You're doing 5, 6, it diverges because it's going to infinity. You add 5, 6 plus 5, 6 plus 5, 6 plus 5, 6, that goes to infinity. So we say, so the series diverges by the K-term test or the test for divergence. Does that make sense to everybody? That's good. Okay, question 4. Please do not, if you are need to go before I do this example, or otherwise stay for the whole example, okay? All right, so when we look at this, if I start doing this, What is wrong with what I just did?
K-term can't prove convergent.
Everything is wrong with what I just did. Does that make sense? So you absolutely cannot do this. If the limit of the sequence is 0, which it is, okay, that part's right. This is not true. The K-term test does not tell you that it converges, right? It just means it could. And so this is real bad. Okay, so you cannot do this. If you do that on an exam, that's the type of thing where you should not only miss all the points for that question, but you should miss like the next 3. Okay, huge deal. Cannot do that. Clear? I'm kidding about missing the next 3, but you cannot do that. Remember that if the limit of the sequence is 0, it could converge like this one does, but it could diverge like this one does. So we don't know. And so this one is too hard for now. We'll do it next week. It turns out this one diverges, but we don't know that from what we've said. Does that make sense? Everybody clear? Okay, I want to answer a question that Gabby asked earlier. Not to single you out, Gabby, but it was a really good question, and now I think it'll make more sense. If you were to split this series, it becomes this. Those are not technically the harmonic series, but the same arguments would apply because this is going to be 1/1 plus 1 over, I guess this one is the harmonic series because it starts at 0. You see what I'm saying? So this diverges because that is the harmonic series because it starts at 0. This one is the end of the harmonic series, which also goes to infinity. So these both go to infinity, but this goes to 3/2. I think you were asking me that, Gabby. Is that right? Okay. Does that make sense?
Is that something we would just have to know based off of what we learned today? Just like
we're going to
something we
talk
didn't
about it
realize?
next week. When you have one that's a lot like the harmonic series, but isn't quite, you use what's called a comparison test. And so the comparison test will prove that these do the same thing. But the fact that this is pretty much 1/k and this is pretty much 1/k does mean they both diverge. And so just it should see these fractions, like these are basically like 1, 1/2, 1/3, 1/4. That first set, that's the harmonic series. And this set, 1/3, 1/4, 1/5, you just lose the first couple terms, but other than that, it's the harmonic series. You see what I'm saying? Yeah, so they both diverge. Okay, I want to talk about what's coming up next. Sorry, I'm holding you to the very last second, but now what we need to do for homework is the series 2 packet. Solutions are provided. I am not going to collect series 1 or series 2, but you should definitely work through series 1 or series 2. It will be very clear on an exam if you have not done those problems. Use the solutions to help you and ask me for help if you need it. We are actually done with material for this week. And so tomorrow, I'm going to offer help session during live lecture. So tomorrow at 1 o'clock, it's going to be question answer. If you have questions, you're welcome to come. If you just want to come listen to other people who have questions, you're welcome to come. It'll just be like an office hour, whoever wants to come. But we're not going to do a new lecture tomorrow because we're done with the week. And so what you should do are series 1 and series 2, those 2 packets. Make sure you're comfortable with all those problems. No WebAssign right now. If you want to take tomorrow off, completely fine. Definitely no lecture Friday, but tomorrow's just Q&A, completely optional. Anyone who can come, I think it'll help if you need to clear some stuff up. Tomorrow's a good time to ask any questions on sequence series that you want to deal with, and it'll be really informal. We'll see how it goes. I'll probably record it, but I'll probably only post it if it's like a lot of examples that are really helpful for everybody. Otherwise, it'll just be like an office hour. Okay? All right, if you have last minute questions, stick around. If not, I hope I'll see you guys tomorrow. Thanks, you guys.